Good evening, and welcome to our third July lecture in physics for 2025. My name's David Jamieson. I'm the MC for this evening's lecture. I'm from the University of Melbourne, the School of Physics, on the land of the Wurundjeri from the Kulin Nation, on where we do our work and live. And I acknowledge their custodianship of our lands going back tens of thousands of years, and don't miss the exhibition on at the newly reopened Potter Gallery on the 65,000 years of cultural heritage. It's a fantastic exhibition. But tonight I'd like to introduce Dr Danielle Holmes, my former PhD student. Danny joined us here in Melbourne for her PhD after a University of Cambridge in the UK undergraduate and master's degree. She was affiliated with Jesus College at Cambridge University, who had the best sporting program of the university, I'm told. Jesus College was founded in 1496, a little bit before the University of Melbourne. She joined us for a PhD from 2017 to 2020. And then even before the ink was dry, metaphorically speaking, on her thesis, she was recruited by my colleague, Professor Andrea Morello at the University of New South Wales, where she moved to become a postdoc and a lecturer from 2020 onwards. In fact, she finished making the corrections to her thesis following the examination whilst in the quarantine hotel in Sydney. And you know, I often dream about locking a PhD student in a room and feeding them through a slot in the door while they finish their thesis. And indeed, that was what was done, but not to be repeated. She's also very active not only in the advanced research program, but in outreach. She was recently on stage for the Sydney Comedy Festival and talking on a science theme, and despite my best efforts, I can't find a video of that on YouTube, but I'm still looking, Danny. However, she also featured in a YouTube video on making Schrödinger cats from implanted antimony atoms in silicon, and those of you who are handy with the internet's probably already found that YouTube video, and it's very amusing. If you haven't seen it, please look it up. Danny is not only speaking to us tonight in our July lecture program, but she's also doing a nationwide tour as the Australian Institute of Physics Marie Curie Lecturer. So if you want to hear the lecture again, she'll be giving it in Sydney, Wollongong and Perth in the upcoming months. So before I hand over to Danny, last week I asked if there was anyone in the audience who'd been to the first July lecture way back in 1968, and I'm pleased to acknowledge Anne Rusden and David Hedger, who were present in 1968 for the very first July lecture in physics. So, and I'm sure there is the occasional person in the audience who've been with us for much of that time as well. So, Danny, please tell us all about it.
Thank you very much, David, for that really warm welcome. And I'm so excited to be here tonight speaking to you all. Apparently, this is the biggest audience that the July lectures have ever had. So this is a huge honor for me to be here tonight speaking to you all and sharing my love for quantum physics out of the laboratory to you tonight. So quantum physics, it's the physics of really tiny things, atoms and electrons, and they behave in completely unexpected ways. And I'm going to tell you a bit about how even these tiny atoms have a huge implication on our universe and look a bit towards shaping our future with new technology. And it's my absolute privilege to be here tonight and being introduced by David Jamieson, because I'm sure as many of you guys know, you'll have seen him speaking at many July lectures in the past, and I've had the privilege to watch him at July lectures recounting many exciting historical facts about physical events. And so it's really my honor to be following in his footsteps as his humble PhD student tonight. And I'm also thrilled to be back at the University of Melbourne, where I did my PhD, because I have many fond memories working in the physics basement in the School of Physics here at the University of Melbourne, with many colleagues that I can see here tonight, fantastic top-tier colleagues, and I spent many hours working away in the clean rooms down there, fabricating devices and measuring them in laboratories. And I spent even longer and harder hours rowing on the Yarra River at Melbourne. So sorry, David, that I was slightly distracted during my PhD. But yes, I had a fantastic time at Melbourne, and now I've jumped ship to UNSW, as David mentioned. And this is me in my day job at UNSW in Sydney, and I get to work with quantum physics on a daily basis, which is a huge privilege. And so I get to play with atoms and electrons and fabricate them inside silicon chips to try and build qubits to make a quantum computer. That's the end goal for our research here. So as you can see, I get to work in a clean room, this very yellow, spooky-looking room, fabricating these silicon chips, and then I get to measure them at super low temperatures in this fancy dilution refrigerator. And these temperatures are so cold, they're colder than any natural place in the universe. And so I think quantum physics is pretty cool, if you pardon the pun. And now, you might not all know, but all of you here tonight, and also all of those of you who are tuning in online, which I hope my parents and my grandparents back in the UK are watching, so hello to you at home. You might not realize tonight, but this is actually just one huge party. And you might be wondering, what party is this? And it is not Christmas in July, even though it is the 25th of July, and I would love a mulled wine right now. But actually, it is the 100th birthday of quantum physics. So it's only right that we celebrate. Woo! Yes, it is the 100th birthday of quantum physics. And that's why 2025 is my favorite year yet, because this is in recognition of 100 years since the birth of quantum physics and celebrating all that it has done for humanity in shaping our understanding of the world around us, and also recognizing that it's helping us shape new technology to be able to achieve really exciting things in the future. So it is very exciting to be here speaking about the International Year of Quantum. And so before we get into what quantum physics is and what is it good for, we need to take a look back to what happened before quantum physics. And this, of course, was classical physics. And classical physics was doing a really great job at explaining pretty much everything around us. We had a really nice idea of how forces affect objects, like that balloon that I just punched into the air. And we had a really nice idea of what gravity does to massive objects too, all thanks to Sir Isaac Newton, who, of course, was famously sitting under an apple tree when an apple fell on his head, supposedly, and he had a brainwave that gravity is a thing. And he wrote down these equations in his Principia Mathematica, which is basically the holy grail for physicists. And so with these equations, we can now really nicely understand forces and objects and how things move. We also had a really nice understanding of electricity and magnetism, thanks to James Clerk Maxwell. And I was speculating, was he struck by a lightning bolt on his head in the same way that Isaac Newton was struck by gravity to discover electromagnetism? And the answer is no. But he was struck by a moment of genius when he managed to formulate his Maxwell's equations, which was a really succinct way of combining the theories of electricity and magnetism together. So thanks to these two founding fathers of classical physics, we had a really great understanding of the world, and we could, as a humanity, we could build new types of machinery and harness electricity to be able to make our lives much easier for us to operate. And so we were very content at this time in physics. We were like, things just work as expected, and we were very happy with it. So much was the contentment in that era that a British physicist, Lord Kelvin, famously quoted, "There is nothing new to be discovered in physics now." And as is often the case with really bold statements like this, it was soon proved to be false. So that's just a warning to people making famous quotes like this. Watch out, because it's going to be proven wrong very shortly. And so in exactly that same year, signs started to show up that classical physics wasn't holding the full picture of the description of our universe. And so what was wrong with classical physics? Well, first of all, it predicted that hot bodies, like our sun, for example, would emit light in an infinite amount of power in the ultraviolet end of the spectrum. And this was a huge problem. It's clearly not physical, because otherwise we would all be sunburnt, no matter how much sun cream we apply. And so it was such a dramatic problem with classical physics at the time that they called it the ultraviolet catastrophe. This is the true name for this problem. So very dramatic. It was a huge problem with classical physics. And this was around the time of 1900 that scientists really started to grind their heads together to try and figure out why this is happening. So clearly, Lord Kelvin's prediction was not true, and there was more to come from physics. And second of all, classical physics predicted that when charged particles orbit, they will decay, so they will lose energy. And so electrons inside all of the atoms in the universe, they would spiral in towards the central nucleus. And so all of our atoms in our universe would immediately just explode in a blink of an eye. And this is quite a bad prediction that classical physics was making, because clearly this was not the case. So scientists around 1900 were getting ideas that classical physics wasn't giving the whole picture, and so they had to come up with new theories to try and explain what was going on. And so first of all, in 1901, just 1 year after Lord Kelvin made his infamous statement, we have this German physicist, Max Planck, who I think he has incredible hair. And he managed to show that if we thought of light, instead of being a wave, if we broke it down into packets of energy called photons, then we would avoid the ultraviolet catastrophe and we wouldn't be sunburnt. So these photons are the quanta that he proved. And so that's where quantum physics gets its name from, these quanta, the individual particles that light is made up of. And so this was great, but it was a huge shock at the time, because physicists were very used to light behaving like a wave. It can diffract, it can interfere, so it was a huge shock to say that light was behaving like a particle. So this completely blew people's minds, but it also very nicely avoided the ultraviolet catastrophe, so maybe it was true indeed. And then second of all, we had a Danish physicist called Niels Bohr. In 1913, he managed to come up with a model that would avoid having all of the atoms exploding within a blink of an eye by saying that the electrons inside the atom could only orbit at very certain distances away from the nucleus. And so that stopped them from decaying and spiraling into the central nucleus, and it fixed these orbits in place. And this was a very nice addition to classical physics, because it managed to explain a really puzzling problem that had been troubling scientists for decades. And this was to do with hydrogen. And so Bohr's planetary model, in which the electron behaves a bit like a planet orbiting the central nucleus, which is the sun, except that the orbits can only be at very particular distances from the sun, it managed to explain why, when you shine electricity through hydrogen gas, you only get 4 colors coming out of it. So we've got red, green, blue, and purple there. We don't get a nice continuous rainbow spectrum like we might expect. And so this had been puzzling physicists for decades. And with Bohr's planetary model, we were able to very nicely answer why this happens. Because the electrons are only allowed to orbit at very certain distances from the nucleus, it means that when they jump between energy levels, they will only emit light of very certain frequencies or colors. So these discrete jumps between discrete levels is what gives us the discrete colors from hydrogen. So this was a huge achievement over classical physics with Bohr's new planetary model of the atom, and it was fantastic. Everyone was really excited about it. The only problem was that it only worked for hydrogen. It didn't work for any other element, so that was rather unsatisfying. And so physicists knew that Bohr's planetary model wasn't the full story as well. But around the early 1900s, physicists were definitely realizing that classical physics didn't hold the whole picture, and that things on the smallest scale, like atoms and electrons, were rebelling against classical physics. And so we didn't have a full picture yet of what was to come for quantum physics, but this happened exactly 100 years ago. So let's take a look at what happened 100 years ago. The birth of quantum physics. And now this was triggered by one particular particle. And it's not the particle that you might expect. Does anyone want to have a guess what particle this is and what could have triggered the birth of quantum physics? Yes? It is not a neutrino. Very good guess, but it is not dust. We're getting closer. What particle would that be? It does. It's pollen, yes. It is pollen. And the reason why pollen created classical quantum physics is actually because it triggered a terrible bout of hay fever in Werner Heisenberg, who is, at the time, picture the scene, it's 1925, it's the summertime in 1925, and a young German physicist, 23 years old, Werner Heisenberg, was struggling terribly with hay fever, all thanks to this pesky pollen grain. And this is actually a magnified scanning electron microscope image of pollen. If you zoom it up, then you can see that it's got a width of about 100 microns, which is about the width of human hair. This pollen was causing him terrible trouble. And he really tried everything, this poor guy, Werner Heisenberg. He started off with aspirin, and that didn't work. So then apparently he tried cocaine, and that wasn't working either. Apparently that was really popular back in the day for Claritin. But eventually he really just gave up, and so much was his frustration that he moved to a secluded island with no trees into the middle of nowhere off the coast of Germany. He went to Heligoland. And in this seclusion on this island where Werner Heisenberg escaped the trees that were causing him such trouble with hay fever, he managed to have the seclusion and the tranquility to be able to have a huge brainstorm and come up with the birth of quantum physics. So he had this flash of imagination where he thought that electrons can't be thought of like regular classical particles where they're just having a continuous trajectory, like we would imagine a planet orbiting the sun, for example, and instead they behave completely differently, and you can't just localize them into this continuous trajectory. And so with this flash of imagination, he was able to put pen to paper and work out the calculations for quantum physics. And it was 3 o'clock in the morning when he finally finished his calculations, put down his pen and looked at his paper in front of him, and he realized the gravity of what he had produced in front of him, which was a new law that described these atoms and electrons on the smallest scale. And he was so excited that naturally he couldn't sleep. And so he went to a top of a mountain nearby and sat there and waited for the sun to rise. And so this was his birth of quantum physics. And ever since then, using his formulation of quantum physics and in future Schrodinger's wave equations for quantum physics, we have been able to explain not just the hydrogen atom like we were able to with Bohr's planetary model, but we could also explain every other atom and subatomic particles and molecules and everything. So this birth of quantum physics was a very pivotal event. And quantum physics is a really beautiful theory, and it's actually our most accurate theory that humans have ever produced. And no experiment that we have performed in the past 100 years has been able to disprove that quantum physics is real. And it is so accurate that it can predict the magnetic properties of an electron to within the accuracy of its measured value to 1 part within 10 trillion. So basically, this is a lot of decimal places, and we know the properties really accurately. And so with this knowledge of quantum physics that explains our smallest scale atoms and electrons, we are able to understand the world around us much better. And so it has enabled many technologies. Did you know that if we didn't have quantum physics, we wouldn't understand how electrons behave in semiconductors like silicon? So we actually wouldn't have transistors that power all of our mobile phones and laptops today. So thank you very much, quantum physics. We also wouldn't understand how atoms behave in magnetic fields and radiation. And so we wouldn't have MRI machines to take images inside the human body. And we also, without quantum physics, would not understand how atoms emit photons of light. And so we wouldn't be able to produce lasers, which, as we all know, we really need to fight aliens. And also really high-speed internet. There's many other applications of lasers. So basically, quantum physics is really beautiful, and it has given us a wide range of applications and technologies from this knowledge. And so by now, you're probably getting the clue that quantum physics is to do with small things. But how small exactly is the quantum world? So I'm going to now take you on a journey into the quantum realm, a little bit like Ant-Man going into his quantum realm, and we're going to see just exactly how small quantum is. So let's start off with a really familiar scale, the human scale. This is me standing in my laboratory at UNSW in Sydney, and I'm about 175 centimeters tall. This is a very familiar scale that we're all used to. So let's zoom in. So if you zoom into a hair on my head, and you image it with a scanning electron microscope there, then you can see that the width of my hair is 1/10 of a millimeter, so that's around 100 microns thick. And we'll continue zooming in even further to the skin on my head, and we'll see an individual skin cell showing up, and that's about 30 microns wide. And now let's zoom in even further. And I promise I did shower this morning, but there is still some bacteria on me. That's kind of unavoidable. All of us have bacteria, good, bad, ugly. They're all always going to be there. And this particular bacteria that you can see is 5 microns in length. So we're getting smaller and smaller. A bacteria is a single-celled organism, but it's different from our human cells, like our skin cells. And let's zoom in on this bacteria even further. And fun fact, did you know that bacteria can also have viruses on them, not just our animal cells? And so this is a virus that is on a bacterial cell. And as you can see, the height of this is 100 nanometers. So we're getting to the pretty tiny scale. A nanometer is a billionth of a meter. So it's very tiny. And most biologists agree that viruses aren't really alive, even though if they infect another cell, like our poor animal cells that you see there, then they can replicate and start producing other viruses. So they're kind of on the cusp of being alive and not really alive at the same time. And this is the kind of scale that we get to when things just are no longer alive. And let's zoom in on the virus even further. So if we look at the head of the virus there and zoom in even more, we might see some molecules wriggling around like tangled strings. And this is, of course, the genetic information of the virus, which is the DNA, that enables it to reproduce and replicate and give us terrible diseases. And also those poor bacteria as well that we're getting infected by viruses. I'm sure they're not having a good time either. But you can see that the DNA molecule, this double-stranded helix, is about 2 nanometers in width. So this is just 2 billionths of a meter wide. So we're getting pretty small. And then all molecules are made up of atoms, of course. So if we zoom into these molecules, we'll be able to see individual atoms of carbon, oxygen, hydrogen, for example. And the average size of an atom is about 1 angstrom. And an angstrom is 1/10 of a nanometer. So that is 10 to the minus 10 of a meter. So we've had to shrink down more than 10 orders of magnitude to go from the human scale all the way down to the atomic world to get to the scale of atoms. And it's only on these tiny scales that quantum physics starts to come into play. And so we can basically forgive the classical physicists back in the day who didn't know about quantum physics and they were just interested in apples and electricity, because it's only at the really tiny scale that we start to notice quantum physics taking part. However, when you do get to this tiniest scale, we actually have quantum things behaving completely differently to how we expect them in our regular lives. So quantum things, like atoms and electrons, they behave both as waves and like particles at the same time. This is called wave-particle duality. And this is kind of crazy to think of in the classical world, like how can something be a wave, like a water ripple on the one hand, or a particle like a billiard ball on the other hand? It just doesn't happen in our lives. But I'm going to prove to you today that it actually does happen on the quantum scale. And we're going to use light to be able to prove this. So we heard previously from that German guy with the amazing hair, Max Planck, that light is emitted in packets of energy called photons. And so I'm going to prove that photons behave both like a wave and also like a particle with 2 simple demonstrations that I hope will work for you tonight. So first of all, to prove that it is a wave, we're going to do an experiment called Young's double slits. And so here we have 2 slits, and we're going to shine light through it and see what happens on the other side. So first of all, let's just imagine what happens if we used regular classical particles like sand, for example, or salt, if you want to be like Salt Bay and just like sprinkle a little bit of salt on there. you've got your two slits, and we want to imagine what is going to happen on the other side. If it was just sand, what would we expect to see? Exactly, two piles of sand. It's nothing too magical is happening so far. We've got two piles of sand happening. So this is what happens with classical particles. Everything just makes sense, and it's just expected. But now I'm going to do it with light, and we'll see what will happen. So in order to make my double slits for this experiment, I'm going to use something really tiny, because light is also very tiny. And so I'm going to use a single strand of my hair. Here's my single strand of hair. And I'm going to shine some red photons on it from a red laser. And I'm going to see what I will get on the wall. So let's see if we can make our pattern show up. Here I've got my red laser. I'll try not to blind anyone, and I'll come into the audience. So as we can see, this is a red laser spot. This is with no hair. And now let me grab a single strand of my hair, trying not to pull it out so that I've still got some nice hair left after the end of this experiment. Okay, I have successfully isolated a strand. Right, so this is what happens without the hair. And then I'm going to show you, hopefully, what happens when I put a hair in front of it. Can you see something happening? So that's with a hair, without a hair. With a hair, without a hair. Let's do it again. With the hair. It's okay, you can see it. I've got a picture that will show it up a bit more clearly in a minute. But basically you can see that there's individual fringes, and it's not just two blobs like you might have expected from classical physics. So I'll show you a better picture of what we were supposed to be looking at there, and show you that this means that light has to be a wave. So this is what we were supposed to see. If it was a perfectly dark room and everything worked really nicely, that is the pattern that you get when you shine a laser at a single strand of hair. And so as you can see, it's clearly not two blobs like we had with sand. It is, in fact, an interference pattern where we've got the brightest blob in the middle, and then we've got some dark fringes and light fringes again, and it goes out to the side. And so the only way we can explain this is if light comes in as a wave, and then it goes through the double slits, and it interferes with itself. So we've got this interference pattern happening where you get bright fringes when you've got constructive interference and the waves amplify, or you've got dark fringes where the waves cancel out and you get destructive interference. So this is very much a wave-like phenomenon, and it proves that photons of light are indeed waves. So hopefully you all believe me on that light behaves like a wave, yes? Amazing. Now I'm going to try and demonstrate that light also behaves like a particle. So this one's a little bit more tricky, but let's see how we go. And so was there anyone back in the history books that could demonstrate that light was behaving like a particle as well? Well, in fact, yes, there was. In 1905, does anyone recognize this guy? Anyone want to guess what his name is? I think you all know, yes, it is Albert Einstein, indeed. So it was 1905 when Albert Einstein was successfully able to explain a phenomenon that had been puzzling physicists for years called the photoelectric effect. And so it was actually this photoelectric effect that won Einstein his only Nobel Prize. So you can forget E equals mc squared, you can forget relativity. It's actually the photoelectric effect that was the most important thing for Einstein to win him his Nobel Prize, because it explained that light behaves as particles. So I'm going to try tonight to demonstrate the photoelectric effect and then explain why it means that light is behaving like a particle. So let's see if it works, because sometimes it's a bit temperamental with the humidity of the room, but fingers crossed we can redo this Nobel Prize winning experiment. And now Einstein himself, he was not really known for being the best experimental physicist in the world. However, he was a really good thinking man. And so he was able to come up with the genius. Hello, the camera's following me, yes? He was able to come up with his genius thought that explained why light is behaving like a particle. So are we able to get the camera onto this photoelectric effect equipment? We've got something called an electroscope, which is a very nice vintage piece of equipment that we've got loaned from the University of Melbourne here. Here's it coming into focus. This is our electroscope. And so we can see in the middle there, inside this glass cylinder, we've got a gold piece of foil dangling down. So this is two pieces of gold foil, and I'm going to charge up the electroscope by putting some electrons onto this piece of zinc metal. So here's a shiny zinc piece of metal. It's about as shiny as my pants. We've got our zinc metal here. I'm going to put some electrons onto it, and I'm going to charge up this electroscope and see what happens to this gold foil at the bottom here. So where can I find electrons from? Well, previously I might have used a balloon to get some electric charge from my hair, but tonight I have the pleasure of using the physics cat, the School of Physics cat. So is this cat called Schrödinger? I'm not sure. However, this is the cat fur that has been very kindly donated by the School of Physics cat in the name of science. So tonight we're going to use this cat fur, kindly donated, and create some static electric charge by rubbing this perspex rod onto the cat fur, and then I'm going to charge up the electroscope. Let's give it a go. And you should all be watching carefully on what happens to this gold foil when I do this. So let's generate some charge with this dead cat. Okay, hopefully we've got some charge coming here. So I've charged it up, and can you see what happens to that gold foil? It's basically repelled itself, and it's now deflected. But previously it was hanging down, now it's gone up. And the reason why is because I transferred some electrons from the dead cat rod situation onto my electroscope. And so because electrons are negatively charged particles and they like to repel each other, as we might know when we rub a balloon on our hair, it all just repels and goes crazy with the static electricity repelling each other. That's the same principle as to why this needle has deflected. And so I've charged up my electroscope. Let's see what happens if I touch the electroscope now. So let's watch the needle and see what happens. Zzz. Just kidding. Oh, okay, I'm good. I didn't get electrocuted. You can see that the needle has gone back down again because the electrons are able to flow away from the electroscope through my body and into the ground. And so I've grounded it. It's all now discharged. So we're going to have to charge it up again to do the next experiment. Let's get some more dead cat fur going. All right. I've given it some electrons. We can see we've charged it up. Very good. Okay, now for the photoelectric effect, the aim of the game is for me to try and discharge this electroscope using photons of light. So first of all, let's try this humble lamp here. So this is just a regular lamp, pretty stock standard photons, visible light going onto the electroscope on this metal tin zinc plate. And as we can see, nothing is happening to my needle. So it's still deflected, which means it's still charged up. And so this light is not doing anything to the system, really. It's just the electrons still live in the metal, and they're not able to escape it. So maybe I need a brighter light. Let's just try and ramp up the power a bit more. What if I go brighter? Nothing's happening. Don't worry, it's not supposed to. No. But let's see. What if I go even brighter? Do we have a bright light around here? Luckily, this is one that Stephen prepared earlier. We've got this. This should hopefully do something, right? So I'm shining it. I'm shining so much light onto it, but nothing is happening. No electrons are escaping this electroscope, and it's still deflected, so it's clearly charged up. So it clearly seems like visible light is not cutting it. But what happens if I use a higher frequency light? So here, I've got an ultraviolet lamp. I can show it to you because it's not on right now. I don't want to blind you guys, but this is an ultraviolet lamp. And we know that ultraviolet light has a higher energy or higher frequency. So let's see what happens if I shine just a little bit of UV light onto here. I'm going to turn it on. And I'm going to put it onto the metal. And you're going to watch what happens to the needle of the electroscope. Oh, something's happening. Can you see? It has gone down. So it's discharged. So previously, we couldn't get anything to happen when we shone really bright visible light onto it. But as soon as I use higher energy UV light, we have successfully been able to discharge our electroscope. And this is the photoelectric effect, where you can get photons of UV light knocking electrons out of the zinc and discharging it, like how I discharged it, how I touched it earlier. So that's the photoelectric effect. I think I deserve a Nobel Prize for that. Thank you very much. And now we'll go back to the slides, please. And I will explain why Einstein was able to show that this meant that light was a particle. So this was a backup in case it didn't work, but luckily you don't have to watch that. That's me in my office back in Sydney doing the photoelectric effect. Okay, so Einstein's genius was that photons were behaving as single particles, and each particle of UV photon could hit out a single electron. So the ultraviolet light has enough energy to knock out a single electron. And so if you irradiate it with UV photons, it'll kick out the electrons and it will discharge. As we saw, the needle went down with the UV light. Whereas if you use visible photons, for example, red light or whatever light we had in our regular lamp, then these individual photons didn't have enough energy to be able to knock out electrons in the zinc plate. And so the electroscope, as we saw, remained charged. And no matter how much light I shone on it, even from that massive, mega, huge, powerful light, nothing happened. And that's not what would have happened if light was behaving like a wave. Because if light was a wave, then over time, even the low energy waves would accumulate enough energy so that they would knock out the electrons eventually. But that's not what we saw. So this is how Einstein demonstrated that light is also a particle. So that's pretty amazing. So now I have effectively demonstrated with you using photons of light one of the most fundamental laws of quantum physics, and that is that small things on the quantum scale, like atoms and electrons, they behave both like a wave, where they can diffract and interfere and produce this interference pattern, like with Young's double slits that we saw, but they also behave like a particle, for example, with the photoelectric effect that we saw. And this will have some huge implications. So what happens when our little particles, like tiny electrons and atoms, are also behaving like a wave? So number one is that waves can be in a superposition of different states at the same time. It's kind of like constructive interference, where you can overlap different waves and have different waves adding up into another wave that's a superposition. And so if we've got electrons behaving like waves, it will be able to be in a superposition of two states at the same time. So we could have an electron that is over here and an electron that is over here at the same time, like instantaneously, which is crazy and not what we would expect in classical physics, because clearly I can't be over there at the same time, unless I had an identical twin, which I do not. However, Susie does have an identical twin, so that would be an amazing thing to show. We should really try that with Susie, to be in a superposition. And so a famous Austrian physicist called Erwin Schrödinger, in 1935, he was having a look into this superposition problem, and he decided that it really was quite crazy. It's a bit like having a cat that is both alive and also dead at the same time. And this is clearly a dead cat. But in, in my research back at UNSW, we have been able to successfully create this superposition of a Schrödinger's cat being dead and alive by having an antimony atom implanted in silicon. So that's the YouTube video you can go and check out there. So superposition is definitely real on the quantum scale, and we can have like a quantum-sized cat would actually be able to be alive and dead at the same time. Another crazy phenomenon that is due to particles at the quantum scale behaving like waves is entanglement. And so entanglement, when we have two particles that are entangled together, they actually behave like a single correlated wave. And that means when you measure one particle, it will immediately affect the state of your other particle, even if they are separated very long distances, for example, on the other side of the galaxy. And so measuring one immediately affects the state of the other one. And even Einstein thought this was pretty crazy. He called it the spooky action at a distance. So it even bamboozled Einstein. However, we know that it is for sure true, thanks to an Irish fellow called John Stuart Bell, who proved that for quantum particles, you can get entanglement, and you can have these crazy correlations that are connecting particles even at a distance. And so by now, you guys might be noticing a little bit of a trend in the development of quantum physics. Can anyone notice a bit of a trend emerging? They're all in black and white, for one, but number two, they are all male. And it is indeed true that a lot of the development of quantum physics in the early ages was done by men. And so even in the first conference that was invented for quantum physics, you can clearly see Marie Curie here is completely outnumbered by men. And so Marie Curie, as we all know, she is famous for discovering radioactivity. She also had 2 Nobel Prizes, both in physics and chemistry. That's rather incredible. And she's also the physicist that this lecture tour that I'm on is named after. So thank you very much, Marie Curie. But it is quite disturbing how outnumbered she is. And so why is this the case? And now, back in the early 1900s, it's true that women were not really encouraged to leave the home and switch it for the laboratory. However, it's definitely not true to say that there were absolutely no women at the time in physics, because we know for a fact that around like a few hundreds of papers were published by female authors at the time for the birth of quantum physics. And so they clearly were there and contributing. It's just that, sadly, nobody has ever heard of them. And this is really unfortunate because it's only now, like in this year and in recent years, that we've started to be able to shed a bit of light on the women that were pioneering quantum physics at the time. And so if there's one thing that comes out of the International Year of Quantum this year, I really hope it will be to shed more light on the hidden figures that were pioneering quantum physics at this time. And so I think it's only right that we recognize a couple of these hidden figures and show the major contributions that they had to quantum physics, even though nobody has ever heard of their name. Like, has anyone heard of the name Lucy Mensing, for example? Because we really should know her name. She is a German physicist, and she was the first person in the whole world to apply Werner Heisenberg's brand new theory of quantum physics to molecules. So here we've got a molecule. She was able to apply it to molecules for the first time in the whole world, which is quite incredible. And as an impressive byproduct of this, she had a huge revelation that the orbital quantum number that basically tells you about the shape of electrons inside atoms has to be quantized into integers. So this is a huge revelation by a person that she had, saying that we have the orbital quantum number either could be 0 for s orbitals that are more spherical for electrons, or it can be 1 in the p orbital that's got this dumbbell shape, or it could be 2, which is the d orbital, and so on. And so she was the first person in the whole world to discover this, which I think is a huge achievement, because it meant that we could understand the electron structure in the periodic table. And so Lucy Mensing, we should definitely remember her name and appreciate what she did for quantum physics. Another really shocking omission from the history books in quantum physics comes from a German mathematician and also philosopher called Greta Hermann. And in 1935, which is pretty much in the early days of quantum physics, it had only been around for about 10 years at this time, she was really pondering about how to relate quantum physics with the reality that we experience. And she was coming at it from a more philosophical perspective, and she was able to show that one of the leading theories for an interpretation of quantum mechanics at the day had a huge error in it. And this was the no hidden variables proof that was written by a great mathematician at the time called John von Neumann. And Greta was the one who actually discovered that there was a big error in this proof. The only problem was that John von Neumann was a hugely famous and great mathematician at the time, so nobody wanted to contradict him at all. It was only Greta that spoke up and said that there was a part of his proof that wasn't correct, and everyone else just ignored it because they were like, John von Neumann, he's the greatest mathematician, we're going to trust him. So sadly, Greta's work was completely ignored. And this was a real big shame because it was only all the way into 1966 when our Irish fellow that we saw earlier, John Stuart Bell, actually discovered that entanglement was real. And he was the one that rediscovered this error in the proof that Greta discovered more than 30 years ago. And so if scientists at the time had listened to Greta and her error that she found in John von Neumann's proof, then we might have understood entanglement 30 years earlier, and we could have been ahead of the game and developing all this cool new quantum technology that relies on entanglement. And so this is a real shame that she was just completely ignored at the time. So I really hope that we continue to shed more light onto these amazing women of quantum physics going forwards and recognize that they did some really important work that just has been ignored in the history books. So that was a little side note. However, I've shown you some very fascinating and mind-boggling effects of quantum particles. So we've had superposition, we've had entanglement, which seems very counterintuitive to our classical understandings. And now I'm going to show to you some examples of how even these tiny particles, like atoms and electrons, these weird behaviors at a small scale can have huge implications on our universe around us. So let's look at some of my favorite examples of the wonders of the quantum world. Number one, quantum physics is actually the reason why stars shine. Did you know that? Let me explain why. So in order to have stars shining, we need nuclear fusion to happen. And so we've got protons that have to come together and combine into a helium nucleus, and that produces energy. This is nuclear fusion. And now the fact of the matter is that these protons are positively charged, and so they don't want to come close to each other, and so they repel each other. And so in order to be brought together to form this helium atom, we actually need to slam them together with super fast speeds so that they can get so close together that they fuse into helium and form energy. And now, an embarrassing fact about classical physics is that it couldn't explain this at all, because most stars are not hot enough to have these protons moving around fast enough to be able to slam into each other with enough speed to fuse to form helium. And so, without quantum physics, we would not have stars shining. And the reason why stars can shine is because these protons are actually quantum particles. And so, let's imagine this is a proton, and if I was in the classical world, which I clearly am, and this proton is just the size of this ball, and I'm trying to get it through an energy barrier. So imagine we've got two protons that need to come together to fuse. There's an energy barrier. It's a bit like throwing this at the floor. And if we wanted it to pass through to the other side, that would fuse together to form helium. But let's just do an experiment and see if this ball will go through the floor. No, it did not go through the floor. That was no surprise to anyone, and that's because we're in the classical world. However, if we were in the quantum world, there would actually be a probability of this ball passing through the floor, or in other words, the protons can come close enough together to be able to fuse together and pass through this energy barrier by an effect called quantum tunneling, which is basically the protons are behaving like waves and they can leak through and fuse together. So it's thanks to quantum tunneling, which is very much a quantum phenomenon, that stars can shine. And it gives us daylight, and so we have all of life on Earth. And so without quantum physics, it would be dark times indeed, guys. We really need quantum physics. So that's my number one favorite wonder of the quantum world. Let's look at number two, which is a little bit closer to home. So this is planet Earth, and it turns out that a number of different forms of life on planet Earth also use quantum physics in order to operate. And now, I know that my granddad is watching at home in the UK, and he really loves bird watching. So what better phenomenon to introduce than navigation of migrating birds? So this is a European robin, and it is very impressive because it can navigate all the way from Northern Europe into the very south of Europe without a map. How does it do that? It can even do it on a cloudy day. And this has baffled biologists for decades. And one of the leading theories as to how migrating birds can navigate so efficiently without a map is actually due to quantum physics. So let's have a look at how quantum physics could help a bird travel. So here's your European robin. And when a photon hits its eye, it generates two molecules. And these molecules have an unpaired electron that is entangled with each other. So these unpaired electron spins are entangled, and if they remain entangled, then the molecules will recombine and emit a photon that the bird can see. So this is what happens if the electrons stay entangled, they recombine and they emit a photon, and the bird actually sees it because it can see a photon of light hitting its eye. However, if the entanglement of the electron spins changes, then it will affect this recombination rate of the molecules, and so it will not produce a photon. And so it's actually true that the Earth's magnetic field can change this entanglement between these electrons. And so depending on the orientation of the bird within the Earth's magnetic field, it will actually change the recombination rate of these molecules that produces photons. And so the bird can effectively see quantum entanglement, which is amazing. And it can use it as a chemical compass to be able to navigate in the Earth's magnetic field. So this is a pretty cool phenomenon, and it's crazy to think that quantum physics is actually helping living life on Earth. So in the last 100 years, we can safely say that quantum physics has really revolutionized our understanding from atoms, subatomic particles, molecules, all the way to why stars shine in the universe and to why birds can navigate on Earth. But in the next few years, I'm really excited because we're in a new stage of understanding of quantum physics where we can actually take quantum physics and harness it for ourselves to build new types of technology that didn't exist before and to be able to solve new types of problems. So let's have a look at my favorite example of one of these futuristic quantum technologies that we can produce. And that is quantum computers. It is a big buzzword, and it is very popular right now, and it is what we are researching at UNSW in Sydney. And I'm going to show you why quantum computers are important for the future and how we can try and build one. So with our classical computers, we know that they store information in zeros and ones. These are those strings of bits, 001, 1001, to type your text messages and send to your friends. And these classical bits are made of transistors, which are either on or off, depending on if a current flows or doesn't flow. And these are classical, they're classical bits. And so the transistor can either be off or it can be on. It can't be anything in between. And so the classical bit of information that it stores is either strictly a 0 or a 1. It's nothing in between. Whereas if we have our qubit or quantum bit, more fashionably known as the qubit, then they can be both 0 and 1 at the same time, because we know that quantum things can be in a superposition of different states. A bit like how Schrodinger's cat is both dead and alive at the same time. This is the poor cat that's in a superposition of 0 and 1 at the same time. And if we can have these qubits that are in a superposition of 0 and 1 at the same time and be able to entangle many of them together, then this will drastically increase our processing power for our computers, and it will enable us to be able to solve different types of problems from what we could before with our regular classical bits. So let's look at the types of problems that a quantum computer would be really good at solving. Number one, and this is probably my favorite one, would be a quantum chemistry application. And so because molecules are just made of atoms and electrons, these are clearly quantum things. And so in order to efficiently simulate them, we need a quantum computer to do that. And if we can simulate molecules, it opens the doors to being able to discover new types of drugs to cure new diseases, or we could also develop materials that could store carbon really efficiently, for example. And so this would really give us so many applications, and it's a very exciting field to be in quantum chemistry. Number two, quantum computers will very radically change how we safely store information. So it will completely change cryptography, and they will be very efficient at machine learning problems, and so it will boost artificial intelligence. Quantum computers will also be really good at handling large data sets. So for example, in weather forecasting, which I know you guys in Melbourne would be really keen for because you guys get 4 seasons in one day. Crazy. So if we could simulate that and forecast it more efficiently, that's a big win for Melbourne. And then, because atoms are quantum and we could simulate their interactions, we might be able to understand how to do nuclear fusion more effectively. And so this might give humanity the chance to be able to harness this unlimited clean source of energy, which would be fantastic for humanity. And this, combined with being able to create new materials that could store carbon capture from the atmosphere, or also store renewable energy, would be able to give humanity a really nice tool in their pocket to be able to help fight climate change, which I think is one of the main problems that we're facing. So as a whole, quantum computers hold a lot of promise, and they will be able to solve really cool problems. So how can we build one as quickly as possible? Well, it is my thought that if we can base a quantum computer as closely off our classical computers that already exist, like our laptops and our mobile phones and our supercomputers, these are all based off classical physics. If we can build a quantum computer using that technology, it will rapidly speed up the progress. So the goal at UNSW in Sydney, in collaboration with the University of Melbourne, of course, is to build qubits using the same platform that our silicon chips are made of for our regular computers. And so this is what we do. We put atoms into silicon, and we make our quantum bits. So I'm going to take you on a little tour through the laboratory, and I'm going to bring you along with me for a day in the life of a quantum physicist. And this is following me around in building a qubit. So how do I do that? So first of all, I've got this nice mirror. Just kidding, it's actually a wafer of silicon, and it's really shiny, so I can look at myself in the clean room. This is a really clean room, as I mentioned before. It's because our devices that I fabricate are so tiny that if we get a single grain of dust on them, it will completely destroy them. So I have to wear this crazy space-like outfit to handle my samples because we want to protect them. They're very precious. So I start off with my silicon chip, and then I shoot a single atom into the silicon chip using something called an ion implanter, which doesn't sound as exciting as an atomic gun. So let's just call it an atomic gun for now. So I get my atomic gun, and I shoot a single atom into silicon. And I do this from group 5 of the periodic table so that it will donate an extra electron. That will become clear later. It matters what type of atom. So I've got my atom in my silicon chip. Then I go into the laboratory, and I pattern these surface metal gates using something called electron beam lithography. And this means that I'm effectively able to control and measure this single atom qubit inside my silicon. And now these gates, this is an actual scanning electron microscope image of my qubit gates that I've fabricated. They're so tiny that each gate, metal gate on the surface, is about 1,000 times the width of a single human hair. So they're so small that you need to use electrons to be able to pattern the features instead of just regular light, because the wavelength is too big for that. So to get the resolution, we use electron beam lithography, which is a very cool technique that I get to pattern these tiny shapes using a finely focused electron beam. And then once I've got my qubit fabricated on my silicon chip with a single atom implanted in there with these metal gates on it that I can control, the next step is to connect up the qubit. So I need to be able to connect it somehow to the outside world to be able to speak to it and get answers back from it. And I do that using a wire bonder. And this little needle here, it can actually bond tiny wires and connect them from my metal gates on my qubit surface to a printed circuit board that I can send electrical signals down and measure it. So here's my wire bonder that I'm using to package my qubit. And this is what I see when I'm wire bonding. Here's my little tiny qubit device in the middle there with the silicon and the metal gates on top. And you can see those tiny little threads are small aluminium wires that connect it to the printed circuit board. So this is what I see when I'm wire bonding. And this is what the qubit sees when I'm wire bonding. So looking back up the microscope, we've got a very flattering zoomed in image of my face. Anyway, that was a digression. So now here is actually a qubit device that I made earlier. So I actually brought one from UNSW in Sydney. This is all packaged up and ready to go. But inside this enclosure is a single silicon chip that has been implanted with a single atom and wired up to connect it to the outside world. And then this copper block is what I'm going to use to put into my dilution refrigerator. All the way at the bottom there, you can see this thing going down. That's called a cold finger. I have to mount this qubit device onto the cold finger in the dilution refrigerator to be able to cool it down. And then I would connect up all of these pins to cables to carry the electrical signals into my qubit. So this is my nice, shiny qubit device. You've all seen a qubit tonight. That's very exciting. And now we cool it down to close to absolute zero temperature. It's actually 100 times colder than outer space. So with this really cold fridge, we need it to be so cold because qubits are really sensitive systems to their environment. And we also want to measure tiny signals, so we don't want any noise to wash out all of that. So once you've got it in the fridge, you put some big vacuum cans around it, seal it all up and close it up. So sadly, quantum computers don't look as cool as this beautiful golden chandelier usually when they're operating, because they're all sealed up and hidden behind these vacuum cans. But we need that to be able to remove the air so that when we cool it down to really low temperatures, it's not just going to frost up. So here's an inaccurate example of what would happen if you cool down the qubit. You get this frost forming with the snowflakes, but that doesn't happen because we don't have any water vapor in the air because we've removed everything in this vacuum. So it's all nice and cold now. We've got our single atom which we know is a donor atom because it's 1 next to silicon in the periodic table. It's not in group 4, it's in group 5. So this means that the atom has an extra proton inside its nucleus compared to the silicon around it. And this positive charge will be able to bind an extra electron to it and localize this electron inside the silicon chip. So it's a really great system because it's actually 2 for the price of 1. We've also got both the nucleus of the donor atom and the electron of the donor atom that we can use as 2 different qubits. So it's great value, guys. This is the platform we should all be investing in. Then what do we do next? We have to apply a magnetic field. So sadly, this bar magnet wouldn't cut it. We actually have a huge solenoid that we put around our fridge to get a really strong magnetic field. And this basically splits the energy levels of both the electron and the nucleus in your single atom qubit, because electrons and nuclei have this quantum property called spin. And when you apply a magnetic field, this spin either points up or down. It's a bit like how a compass needle would point north or south in a magnetic field. So these 2 energy levels are what we use to make our qubit, because spin down could be 0 and spin up could be 1, for example. And so this is our qubit. We've got a qubit on the electron spin and on the nuclear spin, all nicely localized in a silicon chip. So now, how do we actually control this? Because we clearly need to be able to flip from 0 to 1 or vice versa to actually run a useful quantum algorithm to be able to solve a problem. And we do this by shooting it with microwaves that are on resonance with this spin transition. So this is how we can flip the spin from down to up or 0 to 1, etc. And now we can control it to run our algorithms. And then the last piece of the puzzle is, how do we actually measure it? So once we've done our quantum algorithm where we flip the spins from up to down and 0s to 1s and run the quantum algorithm, we need to be able to get the answer out of our quantum computer to tell us whether it's a 0 or a 1 at the end of it. And the way that we do that is with a really cool piece of technology called a single electron transistor, which can detect the spin of a single atom just by converting that spin into an electrical current that we can measure out. And so we can actually read it out visibly with whether the current is high or low, and this tells us whether it's a 0 or a 1 at the end of our operations. So now we've got the whole pieces of the puzzle have come together, and I've showed you how I make a single qubit. But of course, life is not that easy. And in order to have a quantum computer that will solve useful problems, we need actually millions of qubits to make this work. And so this is why we don't have a useful quantum computer yet, and we need to scale up with a huge engineering challenge to be able to have multiple qubits that we can individually control and couple them together. And we envision doing this in our platform by deterministically implanting donor atoms in silicon. Thank you, David Jameson, for your research in this field. And this is our vision, to be able to create millions of qubits in silicon to be able to solve useful problems that will hopefully revolutionize our future. And so, in summary, Werner Heisenberg sneezed 100 years ago. And doing so, he birthed quantum physics. He had this huge revelation that electrons don't behave like classical particles. And from that, we were able to understand how tiny things behave, both as waves and particles. And I was able to demonstrate that with you tonight with the Young's double slit with the laser showing it behaves like a wave, and also the photoelectric effect showing like it behaves like a particle as well. And so with this knowledge of tiny things, we are able to have huge implications on the universe and understand them, all the way from why stars shine to how birds can navigate in Earth's magnetic field. And in the future, I hope that we'll be able to get some really cool quantum technology coming out of harnessing things at the tiniest scale and being able to solve problems like we can't solve already today. And so I think quantum physics is the biggest tool that we have as a humanity, not just to understand the world around us, but also to shape its future with technology. Thank you all very much for listening, and I'll take any questions.
Well, Danny, thank you very much. Thank you very much. I think we've got time for one question from the floor, and if there's anything online, we could take that as well. Is there a question someone would like to ask before we adjourn for some refreshments? Yes, was there a question in the middle? Yes?
Oh, there's a whole microphone and stuff. Hi, thank you so much. That was really, really interesting. This is not a very complicated question. I was just curious from the first image. Why are the quantum computer chandelier things gold? Why not any other color?
Well, gold is really good at conducting heat. And so in order to be able to efficiently cool down your quantum bit to close to absolute zero temperature, you need a really good conductor. So we usually have copper, which is coated with gold. So this is a big copper block, and it's really good at thermalizing, so we can get really low temperatures to have our qubits operating effectively. Yeah, and it looks cool.
It certainly does. So I'm going to now invite you to join us for refreshments over in the Physics Museum. We have an upstairs and a downstairs. Just go up the ramp or go under the ramp, and we've got places where you can grab some food and drink over there. And you'll join us?
Of course.
And so you'll
Free
have
drinks.
an opportunity to talk to Danny up close. So I enjoyed working with Danny. We had a master and apprentice relationship. Sometimes Danny was the master and I was the apprentice. I learned a lot.
True.
So Danny, thanks again
Thank you,
for your
David.
time with us, and thanks for your talk tonight.
Thank
All
you
the
very
best.
much. Thank you. Lovely.